Welcome to Math 1324. This is section 8.5. We are looking at discrete random variables and distributions. Capital X that you see here typically represents a random variable. It's a variable that takes on different values. In this case, it takes on discrete values, fixed numbers. It's not a continuous set of numbers, just discrete fixed values. For example, let's say we talk about the sample space of flipping two coins where we could get heads or tails on each flip. Then my sample space looks like heads, 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 tails, tails, heads, and tails, tails. X, I'm going to let X represent the number of heads that I could get. So X could be 0, means I don't get any heads. I could get one head or I could get two heads. So these are all the values for X, and underneath it we represent the probability of that happening. Since to get 0 heads, there's only one way out of 4, the probability is 1/4. For one head, well, there's two ways to do that, and so that's 2/4, and the way to get two heads is right here, two heads. All right. Now, if you notice, if you add up all these probabilities, and this is a fancy symbol for sum or add things up, all the probabilities have to add up to be exactly 1. Always 1. If it's not 1, then something is wrong. All right, another example. What if we have a 3-child family and we're looking at the gender of the children? So female or male. So this is child 1, child 2, and child 3. I could get female on the first child, female on the second child, and male on the third child. So there are 8 possible outcomes that could occur in my sample space, and I want X to be the number of females in the 3-child family. Well, I might get no females, which means male, male, and male. And there's only one way to do that out of 8. What about one female? Okay, let's see. Female, female, no, can't have that. Female, female, and male. Yes, that would be 1. I could get male, female, male, or male, male, female. So there are 3 ways out of 8. And you can check for 2 females, there's 3 out of 8. And for 3 females, female, 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 there's only one way out of 8. And again, if you add up all these numbers, you get 1 and 3 is 4, 3 more is 7, 1 is 8, 8 over 8, and it adds up to 1. We can form something in this section called expected value. And what expected value is we make another row in the distribution where we take X and multiply it by the probability. So 0 times 1/8, 0. 1 times 3/8, 3/8. 2 times 3/8, 6/8. 3 times 1/8 is 3/8. And so if we add up that whole row, this is called expected value. It's a long-term average. And the surprising thing is it may not be a value that X can take on. So for example, in this one, 3/8, 6/8, 3/8, I get 12/8, which is 1.5, which is a funny number because how can I get 1.5 females? So it's an average and it doesn't have to be a physical quantity. All right, in terms of the homework, let's look here at question 1. They are giving me a probability distribution. These are the values x can take on and the corresponding probabilities. Notice all the probabilities do add to 1. They want us to find the expected value. So we simply multiply x times the probability. I just make one more row. Do this for each of the columns, add them all up, and the expected value here is negative 0.4. So again, you're just multiplying x times the corresponding probability and then adding them all up. Fairly straightforward. All right, in question 2, we draw and keep a single bill, a piece of money, from a hat. And this hat contains one $1 bill, one $5 bill, one $10 bill, and one $50 bill. That's it. There's just one each. So my sample space only has 4 bills in it. X is the value of the money that I can pick out. So a 1, a 5, a 10, and a 50. Well, there's only 4 things in my sample space, and there's only one of each coin or bill, and so the probability is 1/4 for all of them. So what's the expected value? All right, so I make my probability distribution chart. All right, so 1, 5, 10, and the 50 multiplied down. All right, so there's x times the probability. So I take that and I sum that to get e of x, which is the expected value. I get 66 over 4, which reduces to 33 over 2, which is $16.50. So again, there's no bill in the hat that's of that amount. So what is this amount telling me? It tells me that if I kept doing this many hundreds of times, sometimes I'll get a $1 bill, sometimes I'll get a $50 bill, sometimes a 10. And if I took each of those over those mini trials, averaged them all up, on the average I would get $16.50. All right. In question 3, we have a deck of cards. And we're going to draw a single card. If I draw a red card, I'm going to win $5. And if I don't get a red card, I get nothing. Don't lose any money, but I don't get anything. What's the expected value? Well, let's see. S is my deck of cards. There are 52 cards in the deck, 26 red, 26 black. So X represents the money that we're going to earn. If we win, $5. If we lose, $0. So what's the probability of winning? Well, winning was getting a red card. So there's 26 out of 52, which is 1/2. And then 1/2 times 5 is 250 for my row of x times the probability. What's the probability I lose? Well, there's 26 black cards out of 52. and 0 times that number is 0. So the expected value is, well, it's only the sum of one thing because this is 0. And so the expected value is $2.50. Sometimes we'll win, sometimes we'll lose. On the average, $2.50. All right, in question 4, we have an unfair coin. Now that's important because the probability is not 50% for heads and 50% for tails. But if I get a head, I win $1, and if I lose, I lose $1. Probability of head is 0.37. Probability of tail is 0.63. So the probabilities are not the same. So what's the probability that I win? Okay, if I win, that's win. So this is win. That's the probability of heads, which is 0.37. If I lose, I lose $1. And the probability of losing, which is getting a tails, is 0.63. So if I find my expected value, all right, it's the value of x times the probability. Got that? Add them all up. So it's 0.37 minus 0.63. So minus 0.26. So sometimes we win $1, sometimes we lose $1. On the average, we're going to lose 26 cents. That's why they say if you go to Vegas and if you win, quit. Because if you keep playing, you're going to lose, because the house or the casino in the long run will win. That's how they pay for those giant buildings. All right. Let's see. On question 5, it's a bit tricky. So let's take this slowly. We're going to roll 3 six-sided dice. Now, if we roll a 2 at least one time, we're going to lose $20. And if I get in the 3 rolls something other than a 2, I'm going to win $8. So what's the expected value? All right, so we've got lose, which is minus 20, and I've got win, which is 8. Now, in 3 rolls of six-sided dice, by the multiplication rule, there's 6 times 6 times 6. So there's 216 ways. What do they look like? 111, 112, 113, 114. Keep going all the way to 666. Now, I don't think we really want to list all 216. But we need how many ways can we get at least 1, 2? So let's see. What I really want to figure out is how do I not get a 2? So I don't want 1, 1, 2. I don't want 2, 2, 3. I don't want 2, 2, 2. So how many ways is that? Well, if you use the multiplication rule and think of the ways you can get not a 2. So you can get a 1, a 3, a 4, a 5, and a 6. There are 5 possibilities for each one, or 125 ways to not get a 2. So what that means, if there are 125 ways not to get a 2, there are 91 ways to get at least 1, 2. So that's how we get these probabilities of 91 over 216 and 125 over 216. And so then we sum up x times the probability, so minus 20 times this number, 8 times that number, multiply them up, add them, and then we get a decimal that's rather long, but they said round it to the nearest cent, which is minus $3.80. So again, we rounded this by focusing on these two places. The number after the 9 is 5 or bigger, so this number rounds up. All right, in question 6, I have our deck of cards. If I draw a king, I win $10. Otherwise, we lose $4. So kings are good. How many kings are in the deck? Well, there are 4 kings in the deck. Not a king, there's 52 minus 4, or 48 ways not a king. And so if we win, there are 4 kings out of 52, so reduces to 1 over 13. Lose is not a king. There are 48 out of 52, or 12 over 13. Our expected value is multiply each of these. So 10 times 1 over 13 minus 4 times 12 over 13. Simplify this and we get minus 2.92307692. But rounding it to the nearest cent, the number after the 2 is under 5, so we just keep the 92-cent part. So in the long term, if we kept playing that game, we're essentially going to lose minus $2.96. And that concludes our section on discrete random variables.